Okay, let's continue with 11.2, number 4. Show that the harmonic series, okay, which is a summation as n equals 1 to infinity of 1 over n, is divergent. Okay, so how can we show that this thing is never going to converge? It's always going to grow, okay, as we add the terms. So there's a kind of a cool non-calculus based proof of this. We can prove this using the integral test, which is what we'll talk about next. But that requires calculus, and let's prove this in kind of an algebraic way. It's kind of a nice way of going about it. So what is the series itself? The series itself is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus, and it just goes on forever, right? Okay, so let's look at what S of 2 is. S of 2, okay, is the first sum, partial sum of the first two terms. So that's 1 plus 1/2, okay, which is equal to 1 and 1/2. Okay. Okay. Let's look at what S4 is. Okay, let's get the first 4 terms. So we did the first 2. Now I want to do the first 4. Okay, and that's 1 plus 1/2 plus 1/3 plus 1/4. Okay, and I'm going to say that that guy, okay, is bigger than, okay, that guy is bigger than 1 plus 1/2 plus 1/4 plus 1/4. Okay, so all I did was change this 1/3 to a 1/4 and said that that makes it smaller. Okay, would you agree with that? That 1/3 is bigger than 1/4? Yeah, and so what is this? Well, this actually makes things pretty nice in that this is now equal to 1 plus 1/2 plus 2/4, which is 1/2, right? Combine these and you get 2/4 is equal to 1/2, and that's equal to 1 plus 1/2 plus 1/2, that's just equal to 2. Okay. Now I want to go all the way to an 1/8 and see what I get. Okay, so we have this guy, which is 1/2, 1 and 1/2, and then we have 2. And let's go to the next one, which is going to be S sub 8. Okay, and that's going to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Okay, and I'm going to say that that is bigger than, okay, 1 plus 1/2 plus 1/2, okay. Okay, plus is what we got before here. Maybe I'll put in, I won't simplify this yet. I'm going to go 1/4, 1/4, plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8. Okay, so everything that I made the 1/3 Okay, I made the 1/3 and 1/4 into 2 1/4. Okay, the smaller of the two. I turned those guys into, maybe I'll group them, into 2 1/4. And then I took the next 4 terms and I group those and turn all of those into 1/8. Okay, and what do I get by doing this? Well, I get 1 plus 1/2 plus 2/4 plus 4/8. So what am I adding each time? Each time I'm adding an extra 1/2, right? And I'm saying, look, I'm going from 1 and 1/2 to 2 to now this is going to be 2 and 1/2. Okay, to 2 and 1/2. And if I were to do this again with S sub 16, I'm not going to write it out all the terms, but I would get S sub 16 is equal to the first 16 terms. But then I could say that that's greater than, so S sub 16, all this plus the first 16 terms, okay, plus 8 more terms, is greater than, if I turn all the 1/16 and I did 8/16, if I did 1 plus 1/2 plus 2/4 plus 4/8, and then plus 8/16, that would give me 3. Okay, so the idea here, okay, is that S sub 2 to the nth is always greater than 1 plus n over 2. Okay, if I put in 1, it's always greater than, if I plug in 0, it's greater than 1. If I plug in plug in 1, it should be greater than or equal to, sorry. Greater than or equal to 1/2. And then if I plug in 2, then it becomes 2. If I plug in 3, it becomes S sub 8, which would be 2 and 1/2. Okay, so S2 to the nth is always greater than or equal to, okay, this thing. And so what this tells me, this thing keeps growing. Okay, and all I have to do is put on another, I just need to double the number of terms I go out, which I always can because this thing is going to go off to infinity, an infinite number of terms. Okay, so I can always keep doubling the number of terms and just add on another 1/2. And so this thing does not converge, it diverges, it continues to grow without bound. And what we're using here is we're using the idea that if I have a divergent sequence, okay, we'll say that that's B sub n, and that diverges. And A sub n is always bigger than B sub n, okay, then that has to also diverge. Okay, we saw this when we talked about divergent integrals before. Okay, if I have a certain integral that goes off to infinity, and then the other integral is always bigger, then that must also diverge. It also must, because it can't ever go, it has to be bigger than a divergent sequence, which is that one already goes off to infinity. So to sum up, therefore, as n goes to infinity, S2 to the nth goes to infinity, and so S sub n is divergent. Therefore, okay, the partial series is divergent. Therefore, the harmonic series is also divergent. Okay. Okay, so if we look at the terms of the harmonic series, okay, it starts at 1, and then it gets cut in half every, or no, it gets cut in half the next time. If we start it, let's make this 1. Okay, and then we go to 1/2 in our next term, and then we go to 1/3. Okay, in our next term, and then we go to 1/4 in our next term. Okay, so yeah, the terms are going to 0. Okay, the terms do tend towards 0, but they are not going to 0 fast enough. Okay. Okay. Let's look at another theorem here. Let's finish up 11.2 real quick. Oops. Okay, so this theorem, if the series summation n equals 1 to infinity of a sub n is convergent, then the limit as n goes to infinity of a sub n is equal to 0. Okay, so if the series is convergent, then the limit of the individual terms, okay, the sequence, then this is the sequence, must go to 0. Okay, so if it converges, it's got to go down. Okay, you cannot keep adding bigger and bigger items and get a convergent series. Okay, the terms must decrease. I mean, that should be kind of understandable, right? The terms have to get smaller. If the terms that I'm adding, like 1 plus 2 plus 3 plus 4 plus 5, ... if the terms keep getting bigger, there is no way this thing is going to converge to a value. No way it will converge. So here's and it only goes one way. Okay, just keep this in mind. If something converges, if a series converges, then it's a one-way arrow, then we know that the sequence tends towards 0. Or I'll just say the sequence gets smaller. The sequence terms get smaller. The individual terms, sequence terms decrease. Or we could even say the series terms decrease. Okay. If the series converges, then the individual terms of that series must decrease. Now, here's the thing. Okay. Again, this only goes one direction. Okay. My favorite boy band from the 2000s. Okay. It only goes one direction. Okay. If we already know it converges, then we know something about the terms. The terms have to get smaller. Okay. Okay, but here's the big but. Okay. The big but is okay, just because a series, or I'll say just because the terms of a series that just because the terms of a series get smaller does not necessarily mean the series converges. What's a good example of that? What's a good example of a series that, come on, come back. A series that converges or that diverges, but the terms get smaller and smaller. Just because the terms of a series get smaller and smaller does not necessarily mean it converges. Okay, what's a good example of that? Well, we just had an example. We just had the harmonic series is a good example of this. Why? Because the terms in the harmonic series okay, do the terms of the harmonic series, do they get smaller? Yes. The terms of the harmonic series get smaller. So does that mean it converges? Does the harmonic series converge? Sergio says no. Yes, no, it does not converge. Not convergent. Okay. So convergence implies smaller terms. Smaller terms does not imply convergence. However, here's the however. However, we can use this logic in reverse. The contrapositive to help us out. Okay, what's the contrapositive? Okay, it means that if the terms do not get smaller, then the series does not do what? If the terms do not get smaller, then the series does not do what? You know?
They do not converge.
Not everybody at once. I don't want to be talking over each other. Okay.
If they don't get smaller, then the series will not converge.
Thank you, Sekla. Somebody's awake. It's good. Yay. Okay. Okay. Yeah, the series does not converge. What's the word that we use for not converging?
Diverge.
Thank you, Ashley. Yay, another one that's awake. Yay. Okay, good. Somebody drank their hot cocoa. Okay, so yes, it diverges. Then the series diverges. If the terms do not get smaller, then the series diverges. Boom. Okay, very important. And this is such an important statement that we make it its own test. Okay, we we say, hey, this is called the divergence test, or what we call the nth term test. Okay, so the divergence test or the nth term test, okay, says formally that if the limit as n goes to infinity of a sub n does not exist, okay, if there's no limit, or the limit as n goes to infinity of a sub n does not equal 0, okay, so the thing has a limit, but it's not equal to 0, okay, or it doesn't exist, okay, then the series, okay, n equals 1 to infinity of a sub n is divergent. Okay, if this thing does not go to 0 or not exist, then the series is divergent. It cannot converge. Okay, if your terms are not getting smaller, not getting closer to 0, then you're not going to be able to converge. You're going to diverge. Okay. So, divergence test. Nice. Okay, divergence test. Okay, number 5 here. Show that the series summation n equals 1 to infinity of n squared over 5n squared plus 4 diverges. Okay, show that this thing diverges. Okay. Okay, so let's see. Let's just use the divergence test. Let's take the limit of this. The limit as n goes to infinity of n squared over 5n squared plus 4. You can use L'Hopital's on this. You can just do it algebraically. I'll just do it algebraically. The limit as the limit as n squared. I'm just going to divide both top and bottom by n squared. Right? So I'm going to divide everything by n squared, and that's going to give me 1 over 5 plus 4 over n squared. Okay, is equal to okay, 1 over, well, what's the limit of this thing? The limit of that, 4 over n squared. Well, this thing is just going to go to 0. So this is equal to 1/5. Okay, and so that's not the sum of the sequence. Okay, this is just what are the terms going to, the individual terms going to. So they start off, right? They start off, I don't know, as 1 over 9, something like that. Okay, right? So it starts off at 1/9, and then it goes to, I don't know, plug 2 in there. It'll be 4 over, what, 24? So 1/6. And then it just gets closer and closer to 1/5. Basically, it's approximately 1/5 forever. okay? It gets closer and closer to 1/5. And so what are you doing? You're essentially just adding 1/5 plus 1/5. You eventually end up 1/5 plus 1/5 plus 1/5 plus 1/5. So you keep adding 1/5 on. And so this series cannot converge. This series diverges. Since the limit as n goes to infinity of n squared over 5n squared plus 4, okay, is equal to 1/5, which is not equal to 0. So that just means that the individual terms are not getting smaller. They're staying at 1/5 or around 1/5. So you keep adding 1/5 and 1/5. And so if you looked at the sum, okay, the partial sums, S1, S2, S3, okay, you would just keep adding forever. And you would keep adding, and eventually this would become linear because the slope would just be 1/5. Every time you went over, you'd add 1/5. You go over again, you add 1/5. And so eventually this thing creeps up, but it stays at a slope of 1/5. Okay. Delta y there is 1/5. Okay. So for every change in s, okay, we get it, over 1. You know, the change in x here is just 1. The slope is 1/5. So okay, so we keep growing. We grow forever. Grow forever. Okay, I'll finish off 11.2 with one last theorem. So the theorem, if the summation of a sub n and the summation of b sub n are convergent series, so we already know that they converge. Okay. Then so are a constant times either of these. So we would say CAN or CBN. Okay. We could add them together, the series together, they'd be convergent. Okay. Or we could subtract the series and they would be convergent. Okay, either way. Okay. Okay, so I'm going to change paper at this point because that's 11. We finished up 11.2. Okay, we could have possibly gotten there last time, but I had all those technical issues I had to work through. Okay, so let's jump into 11.3 and talk about the integral test. Yes, that's good. Need to get a mouse. Actually works. Okay. Okay, 11.3 is on the integral test. Okay, so that is on the integral test. What is the integral test? Well, okay, if we take a function that represents the series, okay, yeah, the integral test right. Okay, suppose that f is a continuous function, continuous okay, positive decreasing function on 1 to infinity, okay, and let an equal f of n. Okay, so again, this is a subset of the function. Okay, then the series, okay, summation of a sub n equals 1 to infinity, okay, is convergent if and only if, so this is really powerful with the if and only if, because it goes both directions. Okay, so the series is convergent if and only if the integral from 1 to infinity of f of x dx is also convergent. We're basically going to use this in the reverse. We're going to say, okay, we want to prove that the series is convergent, but we're going to take the integral and get the integral, the convergence for and get the integral for the function. And if that converges, then the original series was convergent. Okay. Okay, so this means okay, if the integral from 1 to infinity of f of x dx is convergent, then the summation of n equals 1 to infinity of a sub n is convergent. But what else is nice is if the integral 1 to infinity of f of x dx is divergent, then n equals 1 to infinity of a sub n is divergent. So whatever happens with the integral is also true of the sequence. or sorry, of the series. All right. Wait, let's look at our friend, the harmonic series, right? So we did an algebraic proof of the harmonic series. Let's see what happens with the harmonic series. Number one, test the summation as n equals 1 to infinity of 1 over n for convergence. Yeah, mine?
Sorry, Professor, but kind of like my computer was out battery, so I want to change to another like tool to log in. So can you sign me back later?
Yeah, sounds good. Thank you.
Okay, thank you.
Okay. Okay, test 1 over m for convergence. Okay, so what's the function here? F of x. Well, f of x is 1 over x, right? Okay, so what's the integral from 1 to infinity of 1 over x dx? Well, that's just natural log. So this is going to be the natural log of x to from infinity to 1. What we really do is we use the limit, and we put in a variable, t to infinity, of the natural log of x from 1 to t. This is equal to the limit as t goes to infinity of the natural log of t, okay, minus the natural log of 1. But the natural log of 1 is 0. And what's the limit as t goes to infinity of the natural log of t? That goes to infinity. Okay, why? Because the natural log function continues to grow, okay, forever. And so this diverges, okay, the integral diverges. So since the integral 1 to infinity of 1 over x dx equals infinity, which is divergent, then the summation of 1 over n as n equals 1 to infinity is also divergent. Oh, okay, that was kind of nice. Okay, let's look at number 2 here. Okay, test the series summation n equals 1 to infinity of 1 over n squared plus 1 for convergence. Okay, let's see if this one converges. Okay. So we're going to take the integral from 1 to infinity of 1 over x squared plus 1. What is that integral? It's a famous integral. Anybody know what that integral is?
Tangent inverse.
Yeah, inverse tangent. This is the inverse tangent of x evaluated from 1 to infinity. Right? So this is the limit as t goes to infinity of inverse tangent of x, okay, from 1 to t, okay, which, okay, is the limit as t goes to infinity of the inverse tangent of t minus the inverse tangent of 1. Okay, so let's start with the easy question. What's the inverse tangent of 1? What angle creates a tangent of 1?
Pi over 4.
Yes, very good. Thank you. Thank you, Ling. Okay, pi over 4 is the angle whose tangent is 1. Okay. What is the limit as t goes to infinity of inverse tangent? What's this limit?
Pi 2.
Pi over 2, very good. Yeah, very good, Con. Because it has an asymptote, right? Okay, don't make an asymptote out of yourself by not knowing your asymptotes. Right? So the asymptote for inverse tangent is pi over 2 as we go positive infinity. It's negative pi over 2 if we go negative infinity. Okay, but it is positive pi over 2. So this is just pi over 2 minus pi over 4, which is pi over 4. Boom. Therefore what? Therefore
Very
what?
convergent.
Yeah, therefore, not only is the function convergent when we integrate, this goes to pi over 4, which is convergent, but then we can apply that to the series 1 over n squared plus 1, n equals 1 to infinity, is convergent. Boom. There we go. Nice. Nice, 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 nice. Okay, so we've seen what happens when we have 1 over n. 1 over n was what? Was it convergent or divergent?
Divergent.
It's divergent. What about 1 over n squared? What do you think would happen with 1 over n squared?
Convergent.
Yeah, convergent. Okay, convergent. Okay. What over 1 over n cubed?
Convergent.
Okay. Why?
Because this is a P series, and if the power of the denominator greater than 1 is convergent.
Okay. Okay. Let's see. Let's keep going here. Okay. I mean, I could do the integral, right? I could be like integral of 1 to infinity of 1 over n squared or 1 over x squared dx, right? And that's just going to be x to the negative 2. So this is going to be negative 1 over x from 1 to infinity, right? And so plug in limit as t goes to infinity of negative 1 over t minus negative 1 over 1, okay, is going to be equal to, this thing's going to go to 0, and we're just going to get 1, which is convergent, right? So we could do this for every power if we wanted to, but it would get kind of boring because, as Con says, everything from here on out is going to be convergent. Okay, and we're going to say that the P series, okay, summation n equals 1 to infinity of 1 over n to the P power is divergent for any P less than or equal to 1, and it's convergent for any P bigger than 1. Okay, so this is a P series. Okay, and the way that we prove this is by the integral test. We just, instead of integrating each of these individually, we just take them as a whole and say, hey, okay, what happens if we integrate this and just let P be a variable? It would be an integer variable, okay, or a whole number variable. We're going to take 1 to infinity of 1 over x to the P dx, which is going to be equal to 1 to infinity of x to the negative P dx, which is going to be equal to 1 over negative P plus 1 times x to the negative P plus 1. Okay, evaluated from 1 to infinity, which is equal to 1 over 1 minus P, x to the 1 minus P. I'm going to throw some limits in there. Equals the limit as t goes to infinity from 1 to t now. And this is going to be equal to the limit as t goes to infinity of 1 over 1 minus t, x to the 1 minus t. Oh, no, it's not. I'm sorry. My bad. This is 1 minus p, t to the 1 minus p. There we go. That makes more sense. Minus 1 over 1 minus p, 1 to the 1 minus p. Okay, good. Okay, where, I'll just say this, where P is an element of the natural numbers. Okay, so P is an element of the natural numbers. N. Okay, so let's think about what's happening here. This is 1 over 1 minus P, which is just some sort of constant, times t to the first power over t to the p power, right? Like t to the 1 over t to the p. Okay. If I brought right, so if I subtracted right, it would be t to the 1 minus p, but I want it to be in the bottom. I want it to be in the bottom. So this t to the first. Okay, so what could I do? I could divide both top and bottom by t, right? Boom. And so now that's t to the first and t to the first. Okay, this is the limit as t goes to infinity, and this is equal to 1 over 1 minus p. This is going to be 1 over t to the p minus 1. There we go. Okay, so, and this, again, this goes to infinity, right? So this is the limit as t goes to infinity. So this is really just 1 over some power of t. And so 1 over infinity, that's just going to go off to infinity. So 1 over infinity, that's going to go to 0, okay, which is going to make this whole thing go to 0. Okay, minus 1 over 1 minus p times 1. Okay, times 1 to the 1 minus p. Well, 1 to any power is just 1. Okay, so this is just times 1. So this really equals negative 1 over 1 minus p. Okay, I'm going to bring the negative down below, downstairs, and just distribute it. And so this is just to keep things positive, because, you know, I'm a positive person. So this is equal to P 1 over P minus 1. Okay. So this thing, okay, this thing is convergent, converges to a value if P is greater than 1. If P is equal to 1, diverges if P is equal to 1. Okay. And then what happens if P is less than 1? Right, we can see that this thing is going to diverge because it's 1 over 0, which is, you know, is undefined. So that thing diverges. Okay, what happens if P is less than 1? Okay, well, we go back to our original here and we have kind of an issue, right? We have an issue that if P is less than 1, that means that P is negative, right? Right, and so we would have x to the negative P. Or let's just go back to the beginning. We have n equals 1 to infinity of 1 over n to the negative P. Right, if P is negative, then that's going to give me a negative number, right? Right, isn't that going to give me a negative value? Right, if P is negative, maybe we'll just say that P is equal to negative R. We'll call it R in this case. Okay, because P would be a negative value. What would happen here if we had the summation of n equals 1 over n to the negative R? Well, wouldn't that just be the summation of n to the R? Right? Wouldn't that just be n to the R? Right, so whatever power that is, right, which would be like, you know, n squared or n cubed or n to the 4th, you know, and any of these values. What's going to happen with these series? If I have n squared, n cubed, n to the 4th, is the nth term going to 0? No. So by the divergence test, the limit of n to the r, as n goes to infinity, okay, that just goes to infinity. So that thing does not equal 0. Okay, and so therefore the series would diverge. Okay, so if P is less than 1, it also diverges. Right? So it only converges if P is greater than 1. Okay, otherwise it diverges. So let's formally write that out. Therefore, the summation n equals 1 to infinity of 1 over np is convergent when P is bigger than 1, otherwise it diverges. Okay. Okay, I think we're on number 3, right? Yeah. Okay, so let's do a real easy one. This is a real easy one for Con. Let's see if it's a real easy one for anyone else. Is the series summation n equals 1 to infinity of 1 over n to the 1/2 power. Maybe I won't do that. I'll just do like square root of n, 1 over square root of n. Is that guy convergent or divergent? Is that guy convergent or divergent? Well, this is a p series, even though it doesn't look like it. N equals 1 to infinity of what? This is 1 over n to the 1/2 power, right? Which is equal to the series, n equals 1 to infinity of n to the negative 1/2 power.
Divergent.
Yeah, so p is equal to negative 1/2, right? Is that bigger than 0? No. Not greater. Or sorry, is that bigger than 1? No, it is not. It is not bigger than 1. Okay, therefore, it diverges. Oh. Right. Okay, let's try another one. Okay, since these are so much fun. Okay, determine if the series summation n equals 1 to infinity of natural log n over n converges or diverges. Okay, integral 1 to infinity of natural log x over x dx. Okay, so let's integrate this. Okay, so let's do a u sub. U is equal to ln x. Du is equal to 1 over x dx. Okay, so this is going to be it's just u du, isn't it? It's just u du. Okay, integral u du. I'm going to put x back in, so I'm not going to change my limits. Okay, I'm just going to be like, well, what's the integral of u du? Well, it's u squared over 2, right? But what is u? U is natural log, so this is 1/2 ln x squared. Okay, evaluated from 1 to infinity. Okay. So the limit as x goes to infinity, okay, let's do t this time. Okay. Limit as t goes to infinity of 1/2 ln x squared of 1 to t. Okay. Okay, so this is going to be the limit as t goes to infinity of 1/2 natural log of t squared minus the limit of 1/2 natural log 1 squared. Well, that just goes to 0, so the whole thing goes to 0. Well, I don't need the limit on that. Okay, that thing goes to 0. Okay, and so what happens to the natural log? The natural log goes to infinity. And what's infinity squared? It's just still infinity. So this thing goes to infinity, which is divergent. So therefore, the series ln of n, natural log of n, over n. Okay, maybe I'll put that in parentheses. It's the function natural log of n as n equals 1 to infinity is divergent. Okay, by the integral test. Okay, that is divergent by the integral test. Okay. Let's look at the remainder estimate real quick. Oops. Okay, and the remainder estimate for the integral test. For the integral test. Okay. Okay, basically, how can we get the remainder between the how off are we with our estimation, okay, for our partial sums? Okay. So suppose f of k is equal to ak, okay, where f is a continuous positive decreasing function for x is greater than or equal to n, and the summation a sub n is convergent. Okay, so we already know that the series is convergent. Okay, where the function is based on the sequence a sub n. Okay, and then we add all those terms together, we get the series. Okay, if we define r sub n as equal to the total sum minus s sub n, okay, the total sum minus s sub n, okay, that would be the remainder, right? That would be the error. Okay, this is the error in the first n terms of a sequence. Okay, the error in the first n. What do I mean by that? Okay, let's go back to a sequence that we know works. Okay, so we know that if we have the summation n equals 1 to infinity of 1 over 2 to the n power, we know what this thing equals. Okay, we proved it last time because this was a geometric series. Okay, and so the series, okay, will converge. Okay, and the sum of the geometric series S equals, it was A1 over 1 minus R, right? And we said that last time we would pull off a 1/2 to get the first term. And then 1 minus the common first term is 1/2, and then the common ratio is 1/2. So this is 1. So the sum is 1. Okay. And so it says, what's the remainder? N is going to be S, which is my sum, or maybe I'll call it an S infinity. That's the total sum of the series. Okay. at infinity. Okay, minus S sub n, which is my nth partial sum. For example, in this series, I have 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot, dot, dot. Right? So what would be R sub 4? Well, I'd have to add up and find out, well, what's S? S is 1. Okay. And what's S sub 4? S sub 4 is the sum of the first 4 terms of my series. And that ends up being 15/16. And so R sub 4 is equal to 1/16. Okay, that's the remainder, or the error of just taking the first 4 terms. Okay, that's the remainder or error of just adding the first 4 terms. Now, we don't always have something nice like this. There oftentimes, more times than not, things are not nice. And we don't know what the sum sums to. We just know that it converges. But we have no idea what it converges to. And so it'd be really nice to get a bound on this. So we have error bounds. Just like we had for Simpson's rule and midpoint rule and trapezoid rule, we have error bounds. And the following says that if I take the integral n plus 1 to infinity, the integral of the first n plus 1 terms, or if I start at n plus 1 and go off to infinity of f of x dx, that's going to be less than or equal to the remainder, which is then less than or equal to if I started at the nth term and went to infinity, okay, of f of x dx. Now it has, if this thing is convergent, the terms have to decrease. Okay, otherwise it diverges. Okay, that's divergence test. If the terms don't go down, it's not convergent. Okay, if the terms do go down, well, do they go down fast enough? Is really the question. Okay, if they don't go down fast enough, it's not convergent. And if they do go down fast enough, it is convergent. But we're saying, look, we know this thing converges. Therefore, the terms have to decrease. Okay, so this thing converges to something. Okay, so if we start at n, okay, and we take the integral at n, okay, that's going to give me an upper bound for my remainder. And if I take n plus 1, okay, and go out from n plus 1, okay, that's going to give me a lower bound. Notice the area is smaller if I start at n plus 1. Okay. So let's do an example with this. Number 4. Okay, number 4 says estimate the error in approximating the summation n equals 1 to infinity of 1 over n cubed. We know this converges, it's a p series. By taking by taking s sub 10 as its approximation. Okay, again, this thing converges, but I have no idea what it converges to. Okay, it's not a geometric. It is a p-series, so I know it is convergent, but I have no idea what value this converges to. All I know is that it does have one out there somewhere. Okay, as the terms get bigger and bigger, as n gets bigger and bigger, the terms get smaller and smaller, and they eventually get so small that as I keep adding them, it really doesn't matter. It doesn't change anything. So there is a limit to the value that is being summed up. Okay, but I don't know what that value is, but I can get as close to it as I want. I can get as accurate as I want by taking as many terms as I want to. Okay. All right. I mean, if I wanted to get within 1,000th or 1/10,000th or 5,000th or whatever it is, you know, I could do that. So what? So let's find out, well, what is S10? Okay. What is S10? It's 1/1 cubed plus 1/2 cubed plus 1/3 cubed plus 1/4 cubed plus 1/5 cubed plus 1/6 cubed plus 1/7 cubed plus 1/8 cubed. Come on. 1/8 cubed plus 1/9 cubed plus 1/10 cubed. Okay, and so this is approximately 1.1975. Okay, and if I want to get a more and more exact answer, I just keep adding on more and more and more terms. I just keep going on. Okay, but I want to know how accurate is S sub 10? How accurate, or I'll put about how accurate is S sub 10 to S? Okay, S being the full sum as this thing goes off to infinity. Well, I don't know that. I mean, I could use a computer or a calculator to keep going forever and get increasing terms. I mean, I could try to do that on my calculator and see, you know, where is this thing going to, and how, you know, how close to the value am I really getting to here if I just keep adding on successive terms, right? It'd be 1 plus 1/2 to the third, okay, plus, oops, delete, come on, delete, go back, go over, okay, plus 1/3 to the third, plus 1/4 to the third, oops, left off a 1 there, plus 4 to the third, delete, stop, delete, behave. There we go. Okay, 1/5 to the third. Oops. I want to go back. Okay, second. Insert plus, there we go. Okay, and so let's go to up. Second insert 1. Okay, and we get that, and then we're going to go 1 plus 1 over 6 to the third plus 1 over 7 to the third plus 1 over 8 to the third plus 1, oops, plus 1 over 9 to the third plus 1 over 10 to the third. You could write a computer program to do this for you if you really wanted to. Okay, and then we could just keep going ad nauseum. Okay, 1 over 11 to the third. Okay, 1 over, whoops. Here. Okay, plus 1 over 12 to the third. Okay, and again, we're keep doing this. I don't know if this is going to go to 1.2 or what. Okay, again, I would waste a ton of time doing this. 13 to the third. Okay, which is interesting. And okay, yeah, I don't know where this thing's going. Okay, but I do know that I mean, is it going to go above? More than likely it'll go above 1.2. So I don't know where it's going. Plus, and I don't want to sit here and do this forever to try to figure out, you know, oh, what does this thing really go to? This is a waste of my time. Okay, and plus 1, maybe it goes to 1.2. Who knows? 1 over, maybe 15 to the third is just, it's too big for it to go. All right, I mean, I'll do a few more. Oops. Plus 1 over 16 to the third. Okay, now we're above 2. So 1.2 is not the limit. So again, I don't want to continue to do this and just keep going on forever. The sum could be 1.25 for all I know. Who knows? So I don't want to do it this way. I do want to get the boundary though. Okay. So what is the boundary? Well, we know that R10, okay, the remainder is less than or equal to the integral from 10 to infinity of 1 over x cubed dx, which is a very easy integral to do. Okay, this is super simple integral. Okay, so this is the integral from 10 to infinity of x to the negative third dx, which is going to be, add 1, that's -2. So this is -1/2 x to the -2, evaluated from 10 to infinity. Okay, let me rewrite this as -1 over 2 x squared. Okay, from 10 to infinity. Just the limit as t goes to infinity of -1 over 2 x squared from t to 10 is equal to the limit as t goes to infinity of -1 over 2 t squared minus -1 over 2 10 squared. Okay. So this thing goes to 0. This thing goes to 1 over 2 times 10 squared, which is 1 over 200. Okay, which is 0.005. So I know that the remainder, R10, is less than or equal to 0.005. It's between, it is at most, okay, so the error is at most 0.005. Okay. Now, I could get a bound on that error if I wanted to by looking at the other component here, which is says don't just take n, take n plus 1. Okay, and I say, oh, okay, the error, okay, the boundary on this thing, okay, is if I take the integral n plus 1, right? So we know that R10 is greater than or equal to the integral of n plus 1. Well, what was n? N is 10. So that's 11 to infinity of 1 over x cubed. Okay, so we would get the same thing. This is negative 1/2 x squared from infinity to 1 over x squared. Okay, infinity to 11. Okay, 11 to infinity. We know that when we plug in infinity, this thing goes to 0. And this is going to be 1 over 2 times 11 squared. So this is going to be 1 over 242. Okay, is less than or equal to R10, which is less than or equal to 1 over 200. I don't know what 1 over 242 is as a decimal, but I know the remainder of this 1 over 242 is 0.00413 approximately. Okay, is less than or equal to R10, which is less than or equal to 0.005. So I know that the remainder is between these two values. Okay, it's at most this value, and it's at least that value. So I know that the error in only taking 10 terms is at most 5. Okay, is at most 5 thousandths. Okay, that's kind of cool. So this gives me a bound. This gives me a bound on what my sum would be. So I don't know what my sum was, right? I kept going with the calculator, and I could do that forever. And I'm not, but I could hone in on, if I took more and more terms, I could hone in on exactly what that value is. And how would I do that? Well, okay, what is Sn plus Rn? Does anybody know what that is? The sum of the nth term plus the remainder of the nth term. The sum, or let's say, well, what would be S10 plus R10?
That's the total sum.
Yeah, the total sum. Thank you, Sekla. That's the total sum. That's the total sum S. Right? Now we have this guy here. We have 1 n plus 1 to infinity of f of x dx is less than or equal to Rn, which is less than or equal to n to infinity of f of x dx. Well, what happens if I add Sn to all of these? Let's just go in and add Sn. Sn plus n plus 1 to infinity of f of x dx is less than or equal to S, which is less than or equal to, right? Because again, this would be Rn plus S of n. I won't skip that step. That's important. S of n plus Rn is less than or equal to S of n plus the integral, the error bound, right? We're bounding the error here. F of x dx. Okay, and so this is S of n plus the integral of n plus 1 to infinity of f of x dx is less than or equal to S of n. I'll just make that S now. Okay, so this actually gives me a bound on what my sum would be, which is kind of cool, because I didn't know what the sum was, but the more terms I take, the better I'll get at approximating it, and if I do these integrals, it will give me a bound for what my total sum is. This is a bound on the total sum for a convergent series. And in our case, we had S sub 10 plus Okay, this guy, 11 to infinity of 1 over x cubed dx is less than or equal to the total sum, which is less than or equal to s of 10, integral of 10 to infinity of 1 over x cubed dx. We found these values, so this is a plus. Okay, let's go back to my calculator. Come on, Mr. Calculadora. Okay, I'm going to arrow up here, and I'm going to pull off s of 10. Okay, what was s of 10? Okay, s of 10 was this bad boy here, right? And I'm going to actually store him. I'm going to say, look, let's store that guy and make him alpha A. Okay, store him as alpha A. Okay, and I think it worked. I couldn't really see. Okay, took him. Oh no, did it work? I don't think so. Store, there we go, as alpha A. So now I have s of 10. Boom, I have s of 10 stored in my computer as alpha A. This is approximately 1.19753196, blah, 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 right? Okay. And then what was the lower error bound? Well, I could just take this value, alpha A, okay, and add that to 1 over 242. 1 over 242, right? Boom, and I get 1.201664,217. Let me write that down. Okay, so this guy is 1.201. 1.20166. Oops. Okay, come on, give me back my calculator. 10201664217. 10201664027 is less than or equal to, okay, because again, this was like 1.91975. Okay, plus 1 over 242. Okay, this is 1.1975 forever plus 1 over 200. Okay. Nice. Okay. And so okay. So then let's go back to my calculator. Okay, and let's choose alpha A. Okay, plus 1 over 200. Oops, oh, I alpha locked it somehow. Go back. Plus 1 over 200. Okay, is 1.2025. Okay, so this doesn't tell me what. This does not tell me what it actually converges to, but it gives me a ballpark. Okay. It's 1.2025 31986. Okay. $1.20253196. Okay, so we see that this thing does converge, but it's within the ballpark. Okay, so could we get a better approximation? Could we get a better, boundary? How big is this boundary? Well, it's at least 0.005 away from my, it's within, 5 thousandths, actually it's within 9 thousandths which may or may not be pretty accurate. Okay, it's a boundary. Okay, it's within these two values. Okay, so what would be some quick math that we could do that might give us a better approximation? Well, we know what we would have to do. We would have to add up, you know, S sub something else, and then add that. But the S of 10, that would be the going to like S20 would be the hard part. Because you'd have to know what your partial sum is for S20. Okay, and I think we almost got there. I mean, to get a better approximation. But the integration is actually really, really simple. It's just 1 over 2 to whatever term 1 over 2 times whatever term you're at squared. That calculation is actually pretty simple. Okay, for this particular problem. So if we went to 16, let's just do 4 more here. Okay, this is S sub 16. So let's just go plus 1 over 17 to the third plus 1 over, I didn't do this just for my health, you know, 1 plus 1 over 18 to the third. Okay, plus, second answer, plus 1 over 19 to the third. Okay, plus 1 over 20 to the third. So that's an even better approximation. Okay, we possibly have locked in 3 digits here. Okay, and then I'm gonna hit enter. I'm gonna go up here and grab that guy, hit enter. I'm gonna store that again. We could just store it as alpha A, doesn't matter. Okay, I'm gonna store that in the calculator's memory. Okay, and then we're gonna do what? I would go plus 1 over parentheses 2 times. Now it's the n plus 1th term, so that's 21. So plus 21 squared, right? No, it's just 21 squared. Okay, perfect. Boom. And that gives me that as a lower bound. Okay, so this is 1.2021. 1.2021. Okay, so that's a lower bound. 1.2021. Okay, so lower bound 1.2021. Okay. Whereas before we were at 1.6 and 2.5. Now our lower bound is 2.1. And it may even be the same thing. I'm not going out too much as enough decimal points possibly to get an even better approximation. Come on. Okay, let's see what happens if instead of adding on, instead of adding on, go alpha A, okay, plus this is going to be now 1 over 20 squared, which is what, 400. So 2 times 400 is 800. So this is 1 over 800. Okay, which is boom. Okay, 2022. Nice. So we've pretty much locked in that up to 3 decimal places here. It's 1.202 and then 1 and 1.2022. So, you know, if we went out some more terms, we might even be able to get that locked in between 1 and 2 in our fourth decimal place. We know that it's 0.2021 and 0.2022. So we're 1.2022. So we're pretty locked in there. It's within 1/10,000th. Okay, decimal place accuracy. We're within 1/10,000th because the difference between 0.0001 here and 0.002 here is 1/10,000. So we're locked in. This thing does converge. Don't know what it converges to, but I'm within Okay, 1/10,000th decimal place accuracy. Okay, for the true sum. Okay. Within 1/10,000th accuracy of the true sum. Okay? Okay, that's some good stuff. Okay, let me take attendance real quick. Okay. Oh, good. 31 people are still here. Nice. Okay. So share my screen. I will upload these notes, both 11.2 and 11.1 and 11.2. Let me stop recording real quick.